Good morning, student. In this class, we are going to discuss about the Stokes theorem. In the previous class, we have discussed and have done some problem on Gauss's divergence theorem. Now, let's discuss the Stokes theorem. If you remember, in the discussion of the physical meaning of curl of a vector field, we have found an expression a dot, suppose a vector a dot dr, line integration of a dot dr is equal to divergence curl of the vector a into ds vector. Okay, if you remember, this expression we have already obtained while we discussed about the physical meaning of a curl of a vector field. Here a is the vector field, del cross a means the curl of the given vector field. So a dot dr is equal to curl of the vector field dot ds. Okay, now if we take the closed line integral a dot dr, then on the right hand side we have to write surface integration, because this is the surface element, del cross a dot ds. Okay, this is known as the Stokes theorem. This is known as the Stokes theorem. It's just a restatement of the physical meaning of curl of a vector field. Okay, and similar to the case of divergence of a vector field or Gauss's divergence theorem, this closed integral should this line integral should enclose the surface, otherwise we cannot apply it. So in the Gauss's divergence theorem, the surface should enclose the volume in which we have applied the theorem, and in Stokes case we have to the closed line integral should enclose the surface, otherwise we cannot apply it. For example, let's consider this surface. This is a surface, say S, in the xy plane. Okay, and now if we have to apply the Stokes theorem, now what we have to do, we have to say we start from here, and in order to cover the whole surface area, the first line integral we should do along this path, then the second line integral we should do this path, so third line integral along this path, and the fourth line integral will be along this path. So it should be in the anti-clockwise direction. Okay, so suppose this is a vector field A. The vector field A passes through that surface element S, and we have chosen the line integral along this closed loop. Okay, so for this surface we can obviously apply the Stokes theorem. If in the case our line segment is, for example, it does not enclose the surface, say we have chosen a path like this. Okay, this one, this one, this one, and say this one. So in this case, as you can see, this closed loop does not cover the entire surface, so for that purpose this Stokes theorem will not be valid. So the first point is that the whatever the closed loop we choose for the line integral, it have to surround the whole surface. Okay, so to have a physical understanding of the Stokes law, let's again concentrate on the surface I have drawn here. Here you can see the vector field is along the along the y direction, say, and we are doing the line integral along the four parts. Suppose this is 1, this is 2, this is 3, and this is 4. Okay, now for the part 1, suppose a dot dr, a vector is along this direction and dr vector is along this direction, so this will have positive value. It will be a scalar number, and the scalar number will be positive. Okay, now along this direction, as you can see, the a vector is along this direction, and the chosen path is almost in the perpendicular direction. So for in this path, a dot dr is equal to 0, because there a and dr is perpendicular to each other. Okay, now if we choose the path 3, if these are continuous path, 1 followed by 2, then 3, then followed by 4. Okay, then in the path 3, as you can see, the vector is along this direction and the line integral is along this direction. Okay, so a dot dr, in this case the angle between a and dr will be 180 degree. They are anti-parallel to each other, so this value will be equal to 0. Okay, and again this direction, in the dr and a will be perpendicular to each other along the fourth path, along this direction. So here also the value is equal to 0. Okay, now a dot dr is positive along that path and a dot dr is negative along this path, along the path 3. This is a negative quantity because a and dr are 180 degree to each other. So if we sum up everything, then line integration, the closed line integration a dot dr is equal to 0. Okay, so a dot dr, if a dot dr is equal to 0, therefore the curl of the vector a dot ds will also equal to 0. As you can see, there is no curl here because the vector field is just moving in this direction. There is no circulation of the field lines. So we can say that the curl of this field is equal to 0. Okay, but now let's consider this part. In this part, as you can see, in this part, say a dot dr is equal to positive number here. Then along this direction a dot dr will be equal to 0, and along this direction also a dot dr will be equal to 0, and along this direction a dot dr will be a positive number because the vector is pointing towards negative y direction. This direction we have taken as y, so vector is pointing towards the negative y direction, and the loop will be also against across the negative y, because in this now the loop is along this direction, then this direction, then this direction, and this direction. Okay, so this part it will be 0 because again they are perpendicular to each other, but on the part 3 it will be now a positive quantity because the vector field and also the dr are along the same direction. Okay, so a dot dr is positive here and a dot dr is also positive here. For this path a dot dr is equal to a positive number. Okay, so that means the closed line integration a dot dr is not equal to 0. So that means the surface integration del cross a dot ds is not equal to 0. So there exists some curl in this field. Okay, and this field should be surrounded by this surface. Okay, so that's why we have written it as the surface element S. We don't want the curl outside the surface because it doesn't have any meaning, because we have only considered inside this surface as the surface area is bounded by this closed loop C. Okay, so as you can see, this row is along negative y direction and this row is along positive y direction. So we can say that there is some curl is present within this vector field. So for that reason the curl is not equal to 0, and we have already shown that the line integration, closed line integration a dot dr is not equal to 0. Therefore the field is not curl field. Okay, so this kind of a situation will give you some intuition about the Stokes theorem. Okay, now let's consider this part of this equation. Here you can see a dot dr, of course the line element will be first anti-clockwise along this direction, second along this direction, third along this direction, and fourth along this direction. Okay, so along the path a dot dr is equal to positive. In this direction also, now you see vector is along this direction and dr is along this direction, therefore a dot dr is also positive here, and in this direction a dot dr is again positive, and along this direction now you see vector lines are towards the direction of the line element, so a dot dr is also equal to positive number. So in this case all a dot dr are positive number, therefore there is a presence of heavy amount of curl in this vector field. So this field among these three scenario, if we consider scenario 1, this is scenario 2, this is scenario 3. So if we compare 1, 2 and 3, we can say that the vector field 3 has the maximum amount of curl because the value of the line integral a dot dr is equal to maximum for this surface which is bounded by this closed loop. Okay, so here the surface integration del cross a vector dot ds has the maximum value. As you can see here, there is obviously the presence of curl. If you even see the magnetic lines, vector field direction, you can see there is a presence of curl in here. Okay, so you see the vectors are circling around some point in this surface. Okay, and also if you see this outward field lines, then you can see there is the presence of also a curl field here. Okay, so that's why we have found the maximum amount of curl in this scenario tree. Okay, so this figure basically will give you some conceptual understanding of the curl of a field. When the curl of a field exists, you cannot obviously you will find the circulation of the field lines along certain path not equal to 0. If it is 0, if the circulation is 0, the field is curl free, and if the circulation is not 0, then you can physically see such presence of such kind of vector field, so that there is some curl present into the field. Okay, so in this way we can have some intuitive understanding of the Stokes theorem. Okay, so let me finally rewrite the Stokes theorem again. Line integration, closed line integration a dot dr is equal to surface integration divergence gradient of curl of the vector field dot ds. Okay, and this surface S should be surrounded by the closed loop. Okay, then only we can apply the Stokes theorem. So let me write it down. The surface should be covered by the closed loop. Then only we can apply the Stokes theorem. Apply the Stokes theorem. Okay, and whenever this value, the closed line integration has a finite value or positive value, you can see some circulation of the magnetic field, which you have already seen in this case or in this case. Here the maximum amount of circulation of vector field lines are possible, therefore this field has the maximum amount of torque. Okay, so this is basically the statement of the Stokes theorem, and we'll do some problem, one or two numerical example how to use the Stokes theorem to have any inputs. Okay, so you just remember this: curl of a dot dr is equal to surface integration curl dot ds. Okay, a ds is the surface element and dr is the length element, and this closed loop is enclosed the surface S. Okay, so next part of the video I am going to do some numerical calculation of Stokes theorem. In this part of the video we are going to solve some problems using Stokes theorem. Okay, so let's discuss problem number 1. Problem number 1. Okay, problem number 1 is prove that half into line integration t dot dr is equal to a, where a is the surface bounded by C. Okay, C is a closed line integral. So we are given that half into t dot dr is equal to a, where a is the surface bounded by the loop C. Okay, and further we are given that t vector is equal to minus y into j cap plus x into j cap. So it's a two-dimensional vector. Basically it's in a plane. Okay, xy plane. You see I and j vector are there, so this vector will be in the xy plane. Okay, something like that, this vector. Okay, so since it involves the closed line integral, therefore we have to use the Stokes theorem. And according to Stokes theorem, we know that line integration t dot dr will be equal to how much? Surface integration del cross t vector dot ds vector. Okay, del cross t vector into ds vector. This is the statement of the Stokes theorem. Okay, so now what we have to determine? We have to determine the value of del cross t. That means the curl of the vector we have to determine. Okay, so del cross t vector, what will be its value? I cap, j cap, k cap, del by del x, del by del y, del by del z. Okay, the x component is minus y, the y component is x, and this is z. Okay, so what will be the value? Del by 0, and x does not depend on z, therefore this will be 0, plus j cap, del by del z into y, del minus del y by del z minus del l by del x, 0. So you see this term to that term, right? So here you see y does not depend on z, therefore this value will be equal to 0, and there is 0 here, so 0 minus 0, basically it is 0, plus k vector will be equal to del by del x into x minus del by del y into minus y. Okay, so 0 plus 0 plus k cap, del by del x always give us 1, plus del by del y always give us 1. Since it's minus, minus minus is equal to plus. Okay, so this will be equal to 2 k cap. Okay, so the curl of that vector field is equal to twice k. Okay, now you see this is a two-dimensional vector and in the xy plane. Okay, therefore the surface which this suppose this line integration is always in the xy plane. Since the vector itself in the xy plane, now the normal to this area bounded by this surface will be always in a direction perpendicular to the xy plane. So perpendicular to the xy plane is our z direction. So what we can write, as ds is equal to, ds vector is equal to nothing but ds into k cap, right? So ds into k cap we can write like that. Okay, therefore surface integration del cross t vector dot ds vector is equal to what we can write, 2 into surface integration k cap, since del cross t is nothing but 2 k cap, so k cap into ds into k cap dot ds into k cap. ds is the magnitude and k cap is just direction. Why k cap? Because the vector is in the xy plane, therefore the the closed integral will be in the xy plane and its normal will be in the z direction. So this is k cap. So k cap dot k cap will give us 1, therefore the value is 2 surface integration ds. To surface integration ds means suppose this is the closed surface integration and this is the area. So if its area is a, then surface integration s is nothing but the area of the loop, right? So 2 into a. Okay, so area is equal to half into s del cross t dot ds. Okay, but we know surface integration as del cross t dot ds is equal to this value, so this will be equal to half into line integration t dot dr. Okay, so finally we have proved that a is equal to half into line integration t dot dr, right? So this is the proof. So here we have extensively used the Stokes theorem in order to prove it. Okay, so this kind of proof they may ask in the exam. So this is very simple one, but I mean it's a good chance that you will find it in the examination. Okay, so next I am doing another example, and there can be many other examples, so it's not possible to do everything in the single class. So maybe I can give you some homework so that you can do it at home. Okay, so let me do the second problem number 2. Okay, so the problem is prove that surface integration ds into gradient of a scalar field. Gradient of a scalar field is a vector quantity, so we have write the cross product is equal to line integration phi dr, where phi is a scalar field. Phi is a scalar field. Okay, so we have to prove it. Okay. So let's first write the Stokes theorem. According to Stokes theorem, we know that surface integration del cross A dot ds vector is equal to line integration A dot dr. Okay, we know this is the statement of the Stokes theorem. Okay, so let A vector is equal to phi into c vector. Okay, phi is a scalar quantity and c is a vector. So if you multiply a scalar function with vector, we'll get always a vector, and that vector is A. Here the phi is the same phi which is there in the problem. Phi is a scalar field. So A is equal to phi into c. Let's write it like that. Okay, now what we have to find? Del cross A. So let's see what will be the value of del cross A. Del cross A vector will be equal to del cross phi into c cap. Okay, so you see this is the product of del cross say A into A vector. So A is a scalar and capital A is a the vector quantity. So it will involve two terms, and these two terms will be the first time if we write, then del phi, this is a vector cross C vector. Okay, first term is possible like that, plus phi into del cross C vector. Okay, so from this single term we can make two vector term. First one is del phi is a vector cross C, so it's a vector into vector, to cross product between two vectors is also a vector. So and next is equal to del cross C, it's a curl of the vector multiplied by scalar function. So this is the rule to define such kind of vector product. Del cos phi c is equal to del phi c plus phi del cos c. Okay. Now in this example we consider that, say let C is a constant vector. Let C is a constant vector. Constant vector. That its component does not vary with respect to x, y, and z. Okay. So C is a constant vector. First we have imagined it. A is equal to phi into C, and we imagine that C is a constant vector. We can imagine it. It's not a problem. So if phi is a constant vector, then its curl does not exist, because I mean del cross operator is actually give us the variation of a vector in x, y, and z coordinate. So since C is a constant vector, it does not depend on x, y, and z coordinate system. Okay, sorry, and does not depend on the x, y, or z. It does not change with x, y, and z coordinate. So this term will tend to 0. We therefore write del phi cross C vector. This is nothing but del cross A vector. Okay, so up to until now we have found like this. Del phi C is equal to this vector. Okay, so next step, what we are going to write, okay, so we have to write this expression, right? So del cross A vector dot ds vector. Okay, because this is the statement of Stokes theorem. So let's write it in the form of Stokes theorem. So del cross A dot ds will, what we can write, gradient del cross A is nothing but gradient of scalar function cross phi. So this is in, say this is expression 1. We are putting the value of the del cross A in this expression. So del cross A dot ds is equal to nothing but del the gradient of phi cross product C vector, okay, dot ds vector. Okay, so there is a vector rule. If you remember, A cross B cross C is equal to B dot C cross A is equal to C dot A cross B. Okay, okay, so I mean, since it's a dot product, so the order does not matter. I mean B cross C dot A also equal to C cross A dot B is also equal to A cross B dot C. Okay, so this is the product of vector rule of vector triple product. So del phi we can take it as A, C we can take it as B, and ds both are vector, we can take it as C. Okay, so A cross B dot C is equal to, we can write B cross C dot A, or C dot A cross B, that we can write it. There is no problem with that. So what we are going to write, that using this rule of the vector triple product, we have to substitute or we have to rewrite this expression. Okay, so using this vector product rule, we can write del phi cross C dot ds vector is equal to, what we can write, C dot we can write C dot ds cross del phi, that we can write. Okay, so A cross B dot C is equal to B dot C cross A, that we can write. So A cross B dot C, okay, which we have write is equal to B dot C cross A. Okay, so this rule we have applied. You see, A cross B A cross B dot C is equal to B dot C cross A. Okay, the B dot C cross A, I mean, you just have to rearrange it. Okay, so this rule we can apply it here. Okay, A cross B dot C is equal to B dot C cross A. Okay, similar rule we have applied here. Okay, so now what we can write, therefore we can write del cross A dot ds vector, finally we can write is equal to C dot ds cross gradient of the vector quantity. Okay, so this is the final expression which we have find. So now what we are going to do, we are going to replace equation 2, if this is equation 2, in this form, in Stokes theorem. Okay, so what will be the value? Surface integration C dot ds cross gradient of phi dot ds. Okay, so this value will be equal to dot ds is equal to, what we can write, vector A will be equal to C, there is a phi here and C here, so we can write is phi C vector dot dr vector. Okay, so we can write like that. Okay, now now del cross A dot ds, what we have obtained, del cross A dot ds is equal to C dot ds cross gradient of phi quantity. Okay, so if you remember the Stokes theorem, what it was, surface integration del cross A dot ds is equal to line integration A dot dr. Okay, so in this place now what we have to write, this expression. Okay, so what we will write, C dot ds into gradient of phi, okay, is equal to, since A is equal to what we have written, C into phi dot dr vector. Okay, okay, now you see C is a constant vector, therefore we can take it out from the integrand sign. Okay, along with C we can take out the dot product also, because dot product always involves with a vector. So basically what we have to take it out, C dot, let's put the dot product out of the integration sign, so ds into del phi is equal to, since this is also a C dot product of dr, so we have to put C dot C into dot product outside of the integration sign, so C dot integration phi dr. Okay, so phi is a scalar quantity, so we have to consider the ordinary product between phi and dr. Okay, so now what you can do, we can cancel out this term, we can cancel this term. Okay, so surface integration ds cross gradient of phi is equal to line integration phi dr. Okay, so this is the thing, if you remember, which we need to prove. So hence proved. Okay, so with this I just wind up the discussion on Stokes theorem. There will be some home assignment. I will send those assignment to you. You have to submit the assignment along with the assignment which I have spoken in the last class. Okay, so see you then. Thank you.